Hello, ladies and gentlemen, and welcome to Flight in Space. We're going to talk a little bit about history of space flight today. As you look at your screen, we'll stop at different times with the Edpuzzle for you can answer some questions. But let's talk about rockets. Ancient rockets began in the early 1200 AD of the Chinese. As you can see in this picture here, the Chinese used rockets or gunpowder to help an arrow to fly farther, as they launched them and sent them at their opponents. Um, when we talk about more discoveries that helped us get to space outside of just rockets, Johannes Kepler in 1609 discovered that there was orbital paths that objects traveled around the sun with. He determined that according to their velocity or their speed and direction, as a planet traveled around the sun, it determined its actual path and how long it took to orbit the sun. And he also discovered that the sun was the center of the solar system. Another inventor, or discoverer, I should say, was Sir Isaac Newton. In 1687, he helped us to understand basic laws of motion. Particularly gravity is the one we look at when we talk about force and motion and we talk about flight. And he helped us understand how we could actually get things to move using mathematical formulas to understand the force and the gravity acting upon an object. We look at historical discoveries moving towards rockets. Tversky in 1903, he helped us create mathematical equations for rocketry. He was a visionary that believed that we could get to space. And he actually drew pictures of rockets. And he actually predicted about the Saturn V rocket and that eventually we would be landing humans on the moon, which that actually happened about 65 years later. Moving forward from solid fuel to liquid fuel, Dr. Robert Goddard is known as the father of modern day rocketry. In 1926, he constructed and tested the first liquid fuel rockets, going from a solid fuel to a liquid fuel. From his discoveries, moving further during World War II, the Germans with Van Braun discovered how to create liquid fuel rockets and use them as missiles to attack others. Van Braun worked with Olberth. Later on after World War II, Van Braun came to America and he helped the U.S. develop their Saturn V rocket, which then eventually would take us to the moon. From the 40s and the 50s, there's a lot of great developmental changes and accomplishments in actually leaving the Earth's gravity and getting objects into space outside of our gravitational pull. So why do we use rockets? Well, rockets, as you can see in the list there, for military purposes, atmospheric research, launching probes and satellites, and traveling, and of course, the fun of fireworks. So let me briefly explain a little bit about rockets. The rockets themselves push us forward or upward by producing thrust. Unlike a jet engine, which draws air in from the outside environment, rocket engines use only substances that they carry within them. As a result, a rocket can operate in outer space and thus almost with no air. A rocket can produce more power for its size than any other kind of engine. For example, the main rocket on a Saturn V is only the size of the fraction of the size of a train engine, but it takes 39 train engines to produce the same amount of power that this rocket would produce. Rockets come in all shapes and sizes, from smaller than 2 feet when we talk about fireworks and shooting off rockets for displays, from anywhere from 50 to 100 feet long when we talk about missiles launched at targets during war, to as tall as the Saturn V, which stood 363 feet tall, which is gigantic. Talking a little bit more about the Saturn V. The Saturn V burned more than 560,000 gallons of fuel during its 2 minute and 45-second flight, leaving our atmosphere. The chemical rocket engine became extremely hot from its propellants. The engines can reach temperatures of 6,000 degrees Fahrenheit, much higher than most metals and steel would melt. There are other types of fuels that scientists have discovered for rockets. Nuclear rockets produce heat generated by nuclear fuel to produce thrust, and electronic rockets produce electric energy to produce thrust. We've come a long ways from shooting rockets with arrows to shooting humans into space. When we talk about the NASA Space Shuttle program, this picture you see here, you will notice that this is our shuttle, which would carry our humans and our payload. But these are our rockets on the sides and a fuel container in the middle. Like any good rocket, the energy is produced by burning a fuel, which causes exhaust. And the exhaust pushes out the rear side, as you can see it heating up here, causing an equal and opposite force, Newton's third law, allowing it to launch or take off into space. So let's talk briefly about the difference between a model rocket and a real rocket. They both use the four forces of flight when in our Earth's atmosphere. They both have a very short powered, considerably short amount of powered flight. Solid rocket, when we talk about your model rocket, has a solid rocket, where air rockets that take objects into space uses a liquid rocket. Some have solid fuel rockets when you're talking about those that might hit targets within our Earth atmosphere. Very passive, have no real control once it's launched. The wind can blow it around. Same thing with our real rockets, but they do have some GPS and some navigational controls typically. We talk about low speed and not a whole lot of heat with our model rockets, where we talk about lots of speed and lots of heat or fuel being used to cause lots of heat in our liquid fuel rockets. Relatively inexpensive cardboard, balsa wood, and plastic. When we talk about rockets, especially the ones today being built by SpaceX, very expensive, aluminum, titanium, nickel, things that won't melt at certain temperatures. If we look at comparing the two different types of rockets, this is your model rocket that you might launch in your backyard or out in an open field. You'll notice the bottom of our rocket has fins and a tube which holds everything else, kind of like a fuselage of a plane. We have a solid rocket here, which is removable, so you can add and remove a rocket. When this one's burned up, you can put another one in and launch it again. So it's reusable typically, if you can find it and retrieve it. You'll notice it has some recovery wadding there. That's so when your rocket has this last stage and ejects the nose cone, it doesn't burn up or melt your parachute. So it pushes your parachute and your shock cord and parachute lines. It shoots them up and allows the nose cone to be removed. The nose cone, of course, is aerodynamics, helping it travel higher and faster. But then once it pops off, the parachute is exposed. If you look at the parts of a real rocket, are a structural system you see on the left-hand side there. From the bottom to the top, it looks very similar to our model rocket. We have fins, and we have then our rocket, our propulsion system. You'll notice the propulsion system makes up, in this picture, well over 2/3 or 3/4 of the structure that's there. We've got a lot of fuel. We have an oxidizer, so it can burn the fuel outside of the oxygen of our Earth's atmosphere. And then, of course, pumps and nozzles that eject the fuel out the back. This has a guidance system, so it could have a GPS coordinates, where the missile is going, or it could have humans in there that are traveling in a capsule to go to the to travel to the moon or outside of Earth's atmosphere. This one has a payload. Payload could carry many different things. Could carry satellites, or could carry a warhead that's used as a missile to launch towards your opponents. We talk about the travel of a rocket. Your model rocket here, vertical launch. They both have a vertical launch. As it ascends, it hits a certain level in which it begins to coast, and then that final stage of the solid fuel rocket pushes off the nose cone, the parachute pops out, and it slowly descends back to the Earth. Depending on how the wind's blowing, it could travel many hundreds of yards away from its original launching location. We talk about the flight of an actual liquid fuel rocket. Same principle, has a vertical launch and power descent when the fuel is burning. Once it stages and it disconnects, you have the guidance system and your warhead and your payload that are detached, and they have a second burn to get out into the Earth's orbit, which we'll talk about here in a second. And the rockets from the first stage and the fuel tanks disconnect and they fall back to the Earth. So what is an orbit? If you look at these red lines on the Earth diagram here, you will notice that the are circular orbits or ellipses that travel away from the Earth in continual movement. There is a misconception that outside of the Earth's atmosphere, there is no gravitational pull. But in low Earth orbit, or LEO, there definitely is gravitational pull. It's just not as noticeable from riding in a space shuttle or at the International Space Station, where you've seen videos of astronauts floating along. There still is gravitational pull from the Earth. Let me explain. So, according to Newton's first law, it tells us that if there's no force acting on an object, it will continue to move in a straight line forever. So if no force is acting on a space shuttle, like you see in this picture here, it will never turn and orbit the Earth or the moon. Since we know that's not the truth, we know that there must be some gravitational pull because objects stay in orbit around the Earth. So how does that happen? Well, the Earth's gravitational pull and the force of the velocity or the traveling of that orbital object, in case you see the space shuttle here, it's traveling just far enough ahead and then falling towards the Earth and ahead and falling towards the Earth that it becomes an elliptical orbit. To tell you the truth, when we talk about low Earth orbit, you have to launch an object between 600 and 2,000 kilometers above the Earth's surface, and then it has to travel at least 8 kilometers per second to stay in orbit, to go beyond Earth's gravitational pull. Well, you ask me, what if it's going faster than 8 meters per second? Then it might take a longer orbit, in other words, be further away from the Earth and allow it to continue to travel within that LEO or low Earth orbit. Or if it's traveling fast enough, it will actually fully escape Earth's gravitational pull and be able to travel out within our solar system. So how does that tie in with Newton's third law? Well, of course, we need equal and opposite actions. For every action, there is an equal and opposite reaction. You notice this rocket, the thrust is exhaust being pushed out the back of the rocket, causing the propulsion of our rocket. Depending on how much it weighs, what it's carrying, you need more or less thrust. If you buy a model rocket, they have different sizes of rocket engines, allowing your rocket, depending on the size it is, to travel 5, 6, 7 to 1,500 or 2,000 feet off the Earth. Let's talk about a little bit of a history of what has gotten into space or the orbit around the Earth. The first satellite launched was by the Russians in 1957, Sputnik. It travels about 500 miles off the Earth and travels at 18,000 miles an hour. Sputnik circles the Earth every 96 minutes. Pretty incredible how fast it's traveling. A year later, in March of 1958, the United States launched the Vanguard to be in competition with the Russians and the Soviets. When we talk about the first person to orbit the Earth, in 1961, Yuri Gagarin was a Soviet. We talk about the space race. If you ever watched the movie Hidden Figures talks about some women that were human computers computing uh, mathematical calculations of what it takes to get outside the Earth's orbit or outside the Earth's gravitational pull and get in orbit of the Earth. Um, we as Americans took second stage or second seat to the Russians. John Glenn was our first American in '62 aboard the Friendship to get in orbit around the Earth. We talk about first women in space. First, aka ordinary woman in space, was a textile worker and amateur parachuter who became a cosmonaut. In 1963, Valentina Zabaska spent 71 hours orbiting the Earth 48 times. So, how did we get to the moon? 1961, Kennedy said, "We will travel to the moon." And 8 years later, the Apollo 11 actually got 3 men to the moon. We talk about manned missions. We, in the United States, created NASA, which created the space shuttle program. The space shuttle program, just like any other object, to get into Earth's orbit, has to be traveling at over 8 kilometers per second, um, allowing it to fly in an orbit around the Earth. Once it slows down below that, like any other object, it makes its way back to the Earth. Gravity's pulling it like dropping a rock. Of course, you don't want to drop a rock with people in it, so it uses the principles of an airplane and gliders to slow its descent in a glide. That's why you see the wings, the rudder, the elevators, to fall back to the Earth. The whole objective here is to slow it down, so it uses the Earth's atmospheric air as friction to slow down the speed of this space shuttle. Lots of heat happens with friction. So the bottom part, you see that's black there, of a space shuttle had different types of tiles that would allow it to endure such intense heat. Other manned space flights, back and forth to the International Space Station today, we have the Dragon crew flying with SpaceX, which we'll talk about in a couple of days. But going back and forth to the International Space Station. The International Space Station was built by many trips from our space shuttle program to bring parts and pieces to build this International Space Station, where astronauts spend weeks to months doing tests and observations of the atmosphere around the Earth and space to better understand low Earth orbit. So, other unmanned space flight. Of course, satellites are used to observe the sun, the solar system, and the universe outside of our reach. They can endure the UV rays and X rays that humans' bodies cannot, and also the time away from Earth and not needing food and such. Satellites are used to observe the Earth for various scientific reasons, to look at weather, for military purposes, and also now more and more for telecommunications with satellites and communication, GPS, internet. They also help us better understand the gravitational pull around the Earth and the solar system around. I thought this was interesting. This is a drawing in 1989 about colonizing or living and doing testing on the moon. As you can see, the Earth in the background there. It kind of reminds me of the movie The Martian that just came out in the last 5 years, trying to colonize Mars. As you look at this slide and the next one, in 1995, they made a new rendition. But have we sent astronauts to live on the moon? The answer is no. Later this week, or right after Christmas break, we'll look at Elon Musk has some plans for colonizing Mars and the reality of how soon that could be. But we're 31 years past this first picture, and we have not put people on the moon, let alone put people on Mars. So the future looks great, but there's a lot of work to get there.